Last time, we implemented the list ADT using an array and a variable called length. Today, we'll be looking at a new data structure, the linked list. A linked list is basically composed of multiple nodes. Each node contains a value and a pointer to the next node in the list. A pointer is basically an address that points to the block of memory containing an entity. And in our case, that entity is a node. In code, a node is a structure that looks something like this. This is actually C code. This tells us that there's a structure called node that contains two attributes. Think of a structure as a kind of container of multiple attributes. We also call these attributes either member variables or member fields. They are variables that are associated with a specific object. So our node structure contains one attribute called value, which is an integer in this case. The next attribute is a pointer to another node structure named next. The asterisk next to the node word means that it's a pointer. Hence, from what we said before, each node contains a value, which we can store valuable information, and a pointer named next, which points to the next node in the sequence. Understanding nodes is quite important because we will be using them to make trees and graphs. Okay, now what about linked list? A linked list structure would look something like this. It's very simple. It's simply a structure containing one member variable called head, which is a pointer pointing at the first node of your linked list. Because it's so simple, most people don't bother defining linked list and just use the node directly. So if you want to use a linked list in your code, simply define the head node like so. All right, what happened just now? We created three separate nodes, one named head, one named second, and one named third. Now, let's give the value of the head node 1, and then the second node value of 2, and then the third node, the value of 3. Currently, these nodes don't have their next variable assigned to anything, so these nodes are actually not connected in any way. All right, let's connect them, shall we? Now, we just connected the head node to the second node. So there you go. You actually have a small linked list now of size 2. And the head of your node will be this one because it's the first element. All right, let's attach the third node. Now you have a linked list of 3 nodes. Basically, a linked list does not end until you encounter a node that has null as their next node pointer, because it means it points to nowhere. I showed you how to create a linked list with C because I wanted you to understand it in terms of pointers. But you can create nodes in any other languages. Here's a side-by-side example with C and Python. Remember our lesson about the memory model on how arrays are represented in a different way from a linked list? So unlike arrays, we do not reserve multiple slots of contiguous memory for our linked lists. So the nodes are actually not arranged sequentially in memory. For example, our 3 nodes in the linked list can look like this in the memory, but they can also look like this, or that, or like this. Remember how with arrays, you can quickly jump from the nth element? We do that because we know that each element has a fixed size in memory. For example, if you want to go to index 3 in the array, we can identify that address by adding 3 times the number of bytes for an integer, which is 4 bytes, to our current address. Being able to access a certain element is a specialty of an array, which would be an O of 1 operation. For linked lists, we can't do that, unfortunately. There is no way of knowing what the address of the third node is when all you got is the information of the head node. To get the third element of the linked list, you must traverse from the head of the list, which means you have to follow up the nodes one by one all the way to the third element, starting from the head. And that means traversing a linked list would cost us O of n. Then what's the point of a linked list if it's slower than an array? Well, the advantage of a linked list is that its length can easily change and does not need to be known in advance. In other words, a linked list can dynamically allocate each node. On the other hand, arrays need to be allocated with some fixed amount of memory. Later on, you will also see that linked lists have an advantage for certain operations, such as removing or adding nodes at the front, which can be done in constant time, O of 1. Whereas for arrays, removing or adding an element to the front would be an O of n operation. Okay, now that we know how to create the linked list structure, let's think about how we can perform the following operations on a linked list. Getting the nth element of a list, searching the list, inserting a node at the front of the list, removing a node in the list. We will use pseudocode to explain the detailed steps to implement each operation. This will let you implement these operations in your favorite language as your assignment. So like I said previously, if you want to get the nth element of a linked list, you need to follow up the list starting from the head. Let's look at the linked list. Suppose we want to get the value of the third element. Just to be clear, the head of the linked list is the node number 0. In that case, if we write our function properly, then when the function takes in 3 as an input, it will output 80. When we're writing this function, we would also need to pass in the head of the linked list, which is a node pointer, to let the function know where to get the element from. So let's call this function getItem. And for the input parameters, this function is going to take in a linked list head and an integer n. And it's going to return an integer, which is the value of the nth element. Nice. So we identified what needs to go in and out of this function. Now let's see what goes in the body. We need to use some variables. Let's call them count and current. Let's initialize them by setting count to 0 and current to the head of the linked list. Current will store a node pointer that points to the node we're at. And then each time we move to the next node, we will increment the variable count. Moving to the next node is possible because we can just go to where the variable next is pointing to by assigning next to current. And finally, when we reach a situation where count is the same as the input n, then we return the value of current. Since we kept on tracking the node pointer in the variable current, we can easily access the value and return it. We can do this as long as next of the last node is not null, which means that there is a next node. We can do that by wrapping a while loop around and giving it a condition saying current is not null. If current is at the last node and we put current.next into current, which would be null, then the next loop cannot run because the while loop condition is false. If we come out of the while loop without returning anything, it means that there's something wrong, which can happen when the linked list is too short to return the nth element. For example, when we try to get the 10th element when the 4th node is the last one. So if you would like to do some error handling, this would be a good position to put it. Okay, so we have implemented the first operation. Now let's see how we can implement the search operation. We'll write a function that takes in a value and then returns true if that value is in the list. Just like before, as input parameters, we will pass in the pointer to the head node and also we'll have the value, which we're searching for. So our plan is to go through the nodes one by one and compare each value with x. And if we find it, we will immediately return true. If we don't find it after traversing until the last node, we will return false. Okay, let's call this function search. And for the input parameters, this function is going to take in a node, head, and an integer, x. And it's going to return a Boolean value telling us whether x is in the list or not. We need a variable current, which will play the same role as before, but because we don't need to track the index of the node, we wouldn't be needing count this time. First, we set current to the head node, and we move along the nodes of the linked list by assigning next to current, just like how we did before. So we need a while loop that loops until the end of the list. But this time, we compared the input parameter x to value of current. So if there is a match, we will return true, and all the other cases, including not being able to find a match, will be returning false. So that was how we implement a search by value operation for the list ADT with the linked list data structure as implementation. In the next video, let's learn about some more operations. All right, I'll see you then.